Chapter 7 is about the law of sines and the law of cosines, so we're back to having trig as a part of a triangle. So let's start with just a review of triangles. A triangle that is not a right triangle is called an oblique. And I always spell this word wrong the first time. Did I spell it right? Okay, I did. An oblique triangle. Basically, it's not a right triangle. So before, when we were working with triangles and doing the problems that we had, they were all perfect right triangles, which is why we were able to use sine, cosine, and tangent, because that has to do with a 90-degree angle, all of that good stuff. But we can also solve oblique triangles. Solving means find all of the sides and all of the angles. If at least one side is known and any other two measures are known. So that could be two sides, as long as one of them is a side. So if we think about congruence axioms back from geometry class, you had these three congruence axioms for being able to tell if triangles are congruent. The first one is called side, angle, side. And so if you look at a side and then at an angle and then at a side, you could match up two triangles to decide if that they were congruent if they had matching side, then angle, then sides. Or you had angle, side, angle, so we could have had an angle and then a side and then an angle, and that was another way to determine that two triangles were actually congruent to each other with angle, side, angle. And then the last one is side, side, side. So if all three sides of the triangle were the same length and corresponded to each other, then we could say that those triangles were congruent. Now, these congruence axioms help us determine how to solve these triangles. There are 4 possible cases for solving a triangle. We're only going to be going over the first 2 today, and throughout the rest of the notes, we'll get case 3 and 4. But case number 1 is when you have one side and two angles. So we're talking about one side and two angles, side, angle, angle, or angle, side, angle, because that's one side and two angles. When we have that information on a one particular triangle, we can use what's called the law of sines, which we're actually going to learn about today, to determine the rest of the information. If we have two sides and one angle, and we're specifically going to write it like this, side, side, angle, not the other way around, this is not enough to tell us that triangles are congruent, but it is actually enough information to solve a triangle. But it is going to be a confusing case. It has its own day. We'll get to it eventually. If we have two sides and their included angle, meaning the angles in between them, side, angle, side, or if we have all three sides, we're going to use what's called the law of cosines to solve. And the law of cosines is not till section 7.3, so we're going to take our time to get there. But this table kind of summarizes what you would use given different information in a triangle. As a quick note, if you have all three angles, that's not enough information to solve the triangle because we would need at least one side length. Angle, angle, angle tells us similarity, not congruence, so it kind of doesn't work for either. The law of sines in any triangle ABC with sides A, B, and C, the following hold true. Side length A divided by the sine of angle A is proportional to B over B and C over C. Or vice versa, and we're not going to really write all of those down, but you can do a little something like this. These can all be flipped over to where the sign is on top and the letters on bottom, and those are still proportional. So according to the law of sines, the lengths of the sides of a triangle are proportional to the sides of the measures. In fact, my natural instinct is to put the sign on top, so you'll see me do that a lot, and that's just because the way I memorized these formulas back in the day. We put the sine of A over A instead of A over sine of A, but honestly, either way works. Whatever you see is what you go for. So this law of sines allows us to find missing pieces of information pretty quickly. In this problem here, we're going to be solving a triangle, meaning we're going to find all of the missing information. I highly recommend every time there is not a picture that you draw a picture. So that's what we're going to start with. We'll start by drawing a triangle. It doesn't have to be a right triangle. In fact, it doesn't even have to be like to scale. And we're going to label it A, B, and C. If you're labeling, you could put A on top. I don't care, but as long as you actually label the things correctly. This says that angle A is 32 degrees. it says that angle B is 81.8 degrees, and it says that side A is 42.9. That means that that is the side across from angle A, which means BC, between B and C, is side A. So that's 42.9 centimeters. Great. My first instinct when I look at this picture, since I have it drawn so nicely, is that it's actually very easy to find that missing angle. Why is it super easy to find that missing angle? Yeah, what do all triangles add up to? 180. So just as a reminder for yourself, let's just put that down because it's not like a theorem or anything, but we should just know that all triangles sum to 180 degrees. So that means that we can very easily find angle C. Angle C is just 180 degrees minus 81.8 degrees minus 32 degrees. So beep, beep, bop, we calculate that. That means that angle C is going to be 66.2 degrees. And we already have one part of the triangle that we're missing. I think it's really helpful to add the missing pieces of information to the image as you find them, because then you are completing the entire triangle. Okay, so now that we have angle C, we need to start trying to find the missing side lengths. This is where the law of sines comes in handy. Now, I always recommend two things when it comes to using the law of sines. Again, I'm going to naturally put the signs on top. You can solve them with the letters on top and signs on bottom. It's just my habit and I can't break it. But you're always going to want to use the set that you know both of. Meaning, I know both angle A and side length A, which means I want to include the sine of A over A as part of my proportion. Now again, notice I already put the sine of A above. That's just my habit. Let's solve for B first. So that means that I'm going to put sine of big B over little b. That technically will have one variable because I am solving for little b. This is a proportion, so we solve it like it's a proportion. Here's my second recommendation when it comes to this. Your decimals are going to get super annoying to write down over and over again based on the way that the textbook gives you numbers. We're going to derive the formula first, which means solve with letters, and then plug in at the end, so we only have to put numbers in once. So we cross multiply. A times sine of B is A sine of B. We cross multiply. B times sine of A is B times the sine of A. Remember, our goal is to solve for little b. So what am I going to need to divide both sides by to get little b by itself? Sine of A. So that means that A times the sine of B divided by sine of big A will be equal to little b. Well, now that I have this derived or solved algebraically for little b, I can plug in all the information from my triangle. What's the value of little a? Okay, 42.9 times the sine of big B. What's big B? All divided by the sine of A, which A is 32 degrees. Now at this point, I can shove all of that into a calculator one time, which is why I like doing this bit by bit and solving with the letters first, because writing that many decimals and degree signs over and over again is annoying to me. So I derive with math first and then plug in. And if we plug that in, making sure our calculators are in degree mode, because we're working with degrees, you should get that B is 80.1281 centimeters. Like I said, I like adding that back to the image so we know that this is 80.1281. However your book asks you to round on your homework, you round. Now the last piece of information we need is little c. Since I know the angle across from C, and I know a proportional angle like A over A and B over B, I can use the law of sines again to solve for C. I recommend always including the one that you were given, not the one you solved for, so you don't have to round this number. Meaning, I'm still going to use the sine of A over A, but this time it's going to be equal to the sine of C over C. The capital versus the lowercase letter is actually important here. Angles are capital letters, side lengths are lowercase letters. Again, we are solving for C. I probably should have highlighted that this whole time that we are solving for B. This time we're solving for little c because we want that side length. So we follow the same process. We're going to cross multiply a times the sign of big C equal to little c times the sign of A, and we're still looking for little c here. So we divide both sides by sign of A to be able to solve for little c. It's the same math over and over again, so you might be able to take some shortcuts algebraically once you get comfortable. But if not, go ahead and show all your work so you don't divide by the wrong thing. Now that I have little c isolated, I can plug in what I know. I know that little a is 42.9. I know that sine of c is 66.2 degrees. And we're dividing that by sine of A, which is sine of 32 degrees. We ensure our calculators are in degree mode. We shove all of that into a calculator one time using that fancy fraction to make it easier on ourselves. And we should get that C is equal to 74.0712 centimeters. And voila, that triangle has been solved because we found all of the missing pieces of information. Again, I like adding that information to the image just because it makes it look complete for me, and I feel really satisfied that I know all the sides of that triangle. Questions, comments, concerns about this problem? Feel okay? So some things to remember. The triangles all sum to 180 degrees, so if you know two of the angles, you know the third automatically. When it comes to the law of sines, I want you to always stick with what they gave you because then you're not using a rounded number as part of your proportion for as long as possible. And then deriving with the letters first and plugging in second is just my recommendation. You could obviously plug in all of the numbers here and solve using numbers. I just find it annoying to write numbers that many times. Are we good? Fabulous. Example 2. Let's apply the law of sines to a problem. Let's say an engineer wishes to measure the distance across a river. She determines that angle C is 112.90 degrees and angle A is at 31.10 degrees. She also knows that the distance B, so basically from where she's measured these two paces, is 347.6 feet. We just want to find that distance A across the river. Okay, it already has a triangle drawn, so we don't need to draw one ourselves. We have the information. Let's quickly just figure out what that missing angle is. Since we have two of them, it's almost begging you to solve for that angle. What's the missing angle? 36. We get angle B simply by doing 180 degrees minus 112.90 degrees minus 31.10 degrees, which, yes, ooh, that looks so nice. It's just 36 degrees. So not necessary because it just wants me to find the distance A, but I did need that angle because I had no other perfect proportion to set up. Since I didn't know side length A across from angle A, and I didn't know angle B across from side length B, I have to find that angle so I have a full proportion, B over B. At this point now, we switch to using the law of sines so that we can find little a. The proportion I know the whole thing of is sine of B over B. I found B. I didn't have to round it, so it's a good number to use. And I know little b. And I want to find little a, so I use big A in the sign and little a in the bottom.
It doesn't matter which way you order it.
With, what do you mean? Like, did you put sine of A over A equal to sine of B over B? That's the same thing. Okay. That works. I just naturally put the thing I know all the stuff of first. It really doesn't matter. That's just my habit. So if we derive, remember we are looking for little a, that distance across the river. We would cross multiply. These steps are really going to start looking familiar to you. And then we would solve for little a. So that means we are dividing by sine of B on both sides. Oh, I wrote the wrong letter. Yeah, we're dividing by sine of B. And once it's derived, it's really easy to throw all the numbers in there and put it in a calculator, which means we are doing B, which is 347.6, multiplied by the sine of A, which is 31.10 degrees, all divided by the sine of B, which is 36 degrees. Again, you make sure your calculator is in degree mode. We throw all that in the calculator one time, we should get 305.4636 feet. That's how far the river is across. This next problem is going to look familiar because we solved things sort of like this in chapter 2 of this class, but in chapter 2 of this class, maybe it was 3, we were using perfect right triangles. We were very constricted in the amount of trig that we knew at that time, so we couldn't have solved this problem, but now we have the ability to solve a non-right triangle. It says 2 ranger stations are on an east-west line. So if you were having to draw this image yourself, it would look like this. This is an east-west line, so a horizontal line, 110 miles apart. A forest fire is located on a bearing of north 42 degrees east from A. So here's north. We're going 42 degrees to the east of that. There's the fire. And a bearing of north 15 degrees east. So here's north, 15 degrees more east from the eastern station B. To the nearest 10 miles, how far is the fire from the western station? First things first, which of these letters on this image am I asking you to find? How far is the fire from the western station?
Yeah. So
This is the western station.
just can you find B?
We're trying to find B. Okay, so that's important to know is we're trying to find B here. This is our goal, to find B. To find B, I know that I need to know the angle across from B. So we need to do a little bit of math to know all of the angles in this image so that we can use the law of sines. We'll just go in letter order to keep it organized. If we were finding letter A, and I look at letter A to me looks like there's a right angle here, but we're only not using this much of it because this is angle A. So what would I do to find angle A?
90 minus 42.
Yeah, 90 minus 42. So 90 degrees minus 42 degrees because it's that right angle minus the bearing of 42 degrees east, which means angle A is 48 degrees. Because I'm me, I'm going to draw it in. If we find B, which I know we need for that proportion, but if I find B, B looks like it has a 90-degree angle here. Oops, 90-degree angle here, but then is beyond that 90-degree angle by that 15-degree bearing. So what should I do to find the full angle B? If this much is 90, and it keeps going 15 degrees, what do I do to find the whole thing?
90 plus 15.
Yeah, 90 plus 15 because it's just that whole angle. So this is going to be 90 degrees plus the extra 15 from the bearing, which means that angle B is 105 degrees. So again, I like to add it in that this is 105 degrees. Do we have to find angle C?
No.
Sometimes that would be a no, but we have to know a full proportion to be able to use the law of sines. I'm looking for B, and I know angle B. Do I know side length A across from A? No. Do I know side length C across from C?
Yeah.
Yes, so I actually do need to solve for C here because it's going to be the full proportion I know. Angle C is we're going to use that triangle sum theorem here, which means we're going to do 180 minus 48 minus 105, which is why I knew I needed to solve for all of the angles of this triangle. This is a 27-degree angle. Okay, I know a full proportion now. I know the angle C and I know the side length C. So in my mind, that's what I'm going to write down first. Again, the order you write this down doesn't matter. I like to put what I know first and then what I'm looking for second. What are we looking for again? little b. So that means I have to put sine of big B ahead of it because we're looking for this angle here, or this side length here. So I derive the formula first. I think it's just easier than putting all of those decimals in there. This is C sine of B equal to B sine of C. To solve for B, we divide both sides by sine of C. Like I said, that amount of math is going to get really easy for you soon, where you might be able to go from start to finish without having to show me some work. But while it's our notes, we're going to show all the work. We plug in what we know. We know that C is 110 miles. That angle B is 105 degrees. And that angle C is 27 degrees. Shove that into a calculator, and voila, we would have 234.0398 miles. Now, before you flip for a second, I think there's a couple problems on the homework assignment I'm giving you that you're solving for an angle instead of a side length. So it's not in our notes, it's not in an example, but I want us to write a note to ourselves here in case we need it. Let's say we were solving this proportion for big B. Okay, just let's say we were solving for big B. That means I would have still cross multiplying. Okay, this is a theoretical problem here. And I want B. So right now, what would I actually divide by? Yeah, little c. Now, B is already not by itself. It's tucked into a sine. How do we get an angle out of a trig function? Inverse. So if I was actually looking for angle B, I'd have to take the inverse sine of all of this stuff. Once I have what I'm looking for isolated, that's when I can shove it all in a calculator. So I'm not sure if your homework questions are going to ask you for these. I know our next topic will ask you to solve for angles like this. So just to get ahead of it, we'll discuss here. Again, this is not actually a part of this particular problem, but in theory, if I was asking you for an angle, but you knew two side lengths, you could end up doing this. I don't think it really comes up this lesson, and I know it comes up next time, but just in case you get a homework problem, I want you to be prepared for that. Okay, following the law of sines. Following the law of sines, we get this new way to find the area of a triangle. So when you're in geometry class, you always did that the area of a triangle was 1/2 base times height. Does that sound familiar for you? Well, that height required you to have a 90-degree angle, either the altitude of the triangle or a straight up right triangle, because you needed an actual height of the triangle. And altitude is like from the vertex straight down, making a 90-degree angle. But we're actually able, once we know this trig, to do a little bit more when it comes to the area of a triangle. And it's called, oh, this one doesn't have a name. It's just the area of a triangle. It's like the general version. And there's 3 versions of area depending on what you know. What I notice in these formulas, this is the more general version of the area of a triangle. So we know, oh, that's what I was saying. Okay, here's what I noticed about the formulas. Do you notice how the letters are all different? Yeah. So you have 2 side lengths and a separate angle. This is actually going to end up being the angle in between the side lengths. So this comes from side angle side. So we have 2 sides and the included angle that can allow us to use these formulas just to really quickly find the area of a triangle. So the area is half of the product of the length of the 2 sides and the sine of the angle between them. In my mind, the way I remember this is whatever 2 side lengths I know, the angle I'm using is the different letter. They're all different letters here. No matter what order or what you know, it's always the included angle. So if we're finding the area of this triangle, oh look, it gave us a nice picture. But wouldn't you know it, in the picture, what is one of these angles measured in? What is that called? Degrees and minutes. Yuck. When we're using our calculator, because there's no degrees and minutes button, we do need to change it just to degrees. So to do that, remember it's the degree plus the minutes divided by what? 60. And we're going to leave this one in fraction form because I don't want to round this number and then use a rounded number within my problem. So we should get that it's kind of ugly, 331 over 6. I know that that's a decimal approximation we could use. If it was a final answer, that would be fine. But because we want to use this number, we want to use the whole number. So we're going to leave it in fraction form instead of chopping it off by decimal approximation. Okay. So we're going to find the area of this triangle. I'm going to use the area formula, and I'm going to make sure we can pick the right one. So what side lengths do we know? A, B, or C? A and C, which means it's going to be 1/2 A times C times the sine of B. Obviously, I know it's the two sides I was given and the angle included between them. So now that we have it derived for area, it's exactly what we want. We can plug in what we know. We know that the A side length is 30.0 feet. The C side length is 42.0 feet. And angle B is 331 over 6 degrees. You throw all that into a calculator, again in one fell swoop. This is really why you don't want to use a rounded number here, because you'll get a different answer if you use the rounded sign. We should get that the area of this triangle is 586.0634 square feet. Easy peasy. We didn't have to spend time like you did in geometry class drawing an altitude and figuring out the height using sine, cosine, and tangent. We were able to just answer the question using this area of a triangle. So if we try another one, again, we're going to find the area of a triangle. The problem is with this image, I don't know two side lengths and an angle in between them. I know two angles and a side in between them. So I actually have to do a little bit of work to find one of those two missing sides before I can plug it all into the formula. So we need to make it so where we have a side angle side piece of information, which means we're going to need to use the law of cosines, which means that we need to know a full proportion, which means we're going to find angle B. Okay? Before we really get into finding angle B, let's quick change these from degrees, minutes, and seconds into degrees. 24 degrees and 40 seconds is 24 degrees plus 40 divided by 60, which again, because we're going to use it in a problem, I don't want to round. We're going to use the fraction 74 over 3 degrees. And angle C would be 52 degrees plus, again, 40 over 60, which is 158 over 3 degrees. All right, that's enough information for us to find angle B. How would I find angle B, y'all? Yeah, it's all the triangles add to 180 theorem. So I can take 180 and I can subtract 74 over 3 and subtract 158 over 3. Again, this is why we don't want to use a rounded number because we'd get a rounded B. But B is going to be 308 over 3 degrees. We're going to leave it as that funky looking fraction because we want a pure number here. So I know that this is 308 over 3 degrees. Now that I know a full proportion, I know big B and I know little b, I can pick which of the two sides I want to use. Do y'all care if we use A or C?
Doesn't matter.
Doesn't matter. Great. We're going to find C because that's what I did in my notes when I practiced this problem. So we have the law of sines. Sine of B over B is proportional to the sine of big C over little c. Our goal is to find little c. Our goal is to find little c because then we would know a side, angle, side, and be able to find the area pretty quickly. So again, especially on this one, because this is a fraction and a fraction, I am not plugging those numbers in first. I am deriving the formula, which means solving using letters. We're still looking for little c, which means b times the sine of big C over the sine of big B will be our c value. And we can plug in everything we know. C is going to be little b, which is 27.3, times the sine of big C, which is 158 over 3, 8 over, that is the weirdest looking 8 I've ever written in my life. Let me try that again. 158 over 3 degrees, all divided by the sine of B, which we found to be 308 over 3 degrees. Glad we didn't type those numbers in early, because that's a lot of fractions to be moving around your paper. But when you throw that into a calculator, you should get 22 point, and I'm going to be aggressive with the number of decimals that I'm writing down, because I really don't want to round this number too soon. It's in the middle of a problem. It's not the end of the problem. Now that I know a side, an angle, and a side in that order, I can use that side, angle, and side in the area formulas that are at the top of this page. Which means I am using the area is equal to 1/2 side length B times side length C times the sine of angle A. That's the two sides and the included angle. So this is going to be 1/2 times 27.3 times this number. I'm going to be lazy for a second. Multiplied by the sine of A, which is 74 over 3 degrees. When we calculate this, you want to not lose any of those decimals if we're really, really wanting an accurate number here. It's not science. We're not using significant figures. We're going to make sure we have the most accurate number as possible for us. And when you throw all of that into a calculator, you'd get 126.7410 centimeters squared. And this is the final answer, which means, yes, you actually round this one. Your book may have you round to different numbers, so just make sure you're paying attention to what it's wanting you to round to in the answers. So when finding the area, just as a quick recap, you could be given enough information just to throw it into the formulas like we did in example 4, where we had enough information immediately, or you might have to use the law of sines to find a side, angle, side relationship so that then you can use the formula from the top of the page. Just depends on what you are given in each particular problem. Any major questions before we stop listening to me talk? Fabulous.